For this example, we're going to sketch the graph of a rational function with correct behaviors at zeros, holes, and vertical asymptotes, as well as correct end behavior. Now, this rational function is given where the polynomial is both expanded on the top and bottom, as well as factored on the top and bottom. But it's the factored form that we're really going to be working from. So we see here in the factored form that there is a factor that's on top and bottom that cancels out. So we're going to go ahead and do that reduction here so that we have x plus 1 left on the top and x times x minus 2 left on the bottom. The x minus 3 that appears on the top and bottom each once is going to cancel out completely. But to make this equal sign make sense, we've got to keep the information that was coming from that factor. And that's the fact that x cannot equal 3, because if we were to plug in 3, we'd be dividing by 0 in the previous step. The reduced step, we lose that information, so we've got to hold on to it. So we have to say x cannot equal 3. Now, the end behavior is what I want to tackle first. And the end behavior is going to be coming from the ratio of the dominating terms. And so we can get that ratio either from the expanded form, fairly easily from the expanded form, but if all that you have is the factored form, we can get it that way too. And what we do is we just drop out in each factor all of the lower power terms. So on the top we just have the x because the plus 1 drops out. On the bottom we've got an x times an x because the minus 2 part drops out. So we are looking at x over x squared, which we could reduce to 1 over x, and the behavior of 1 over x has a horizontal asymptote that's the x-axis. So that would be the horizontal asymptote y equals 0. That's the x-axis. Okay, so there's our end behavior, and so now let's take a look at zeros. So zeros would be wherever the top is equal to 0 within the domain. So the top is x plus 1 in our reduced form equal to 0. And so when we subtract over the 1, we've got x equals negative 1 is going to be our root, our 0. And that 0 has, the behavior at the 0 is that it's going to cross because the factor x plus 1 has multiplicity 1, which is odd. So just like polynomials, we're going to see the crossing happening at that 0. So now holes would be the next thing that we look at. And holes would be kind of a minor discontinuity for a rational function. And holes are always coming from that additional piece of information that we had to throw in so that our equal sign makes sense. So that x not equal to 3 is telling me that I have a hole whenever x is equal to 3. Well, that's fine. We know that the hole has that x value, but I need to now know what the y value that goes along with that hole is. And so the way we get the y value is we plug in that forbidden value from the domain, not into the original function because we know that's going to give us problems since it's not in the domain. But what we do is we plug it into the reduced form. And so we can plug that in to the x plus 1 on the top, so that would be 3 plus 1 on the top. And on the bottom, we plug it into x, so that'd be a 3, and then times x minus 2, so that'd be a 3 minus 2. So on the top, that gives us 4. On the bottom, it would be 3 times 1 when we do the subtraction, so it would be 3. So overall, the hole is going to be located at 3, 4/3. And so finally, we are at vertical asymptotes. All right, so vertical asymptotes happen whenever we have a factor in the bottom that remains in the bottom after we've done the reduction. And so we have two factors in the bottom. We've got x and we've got x minus 2. We set each one of those equal to 0 and solve, so x equals 0 is already solved, and we've got x equals 2. Those are going to be our vertical asymptotes. And notice that those two factors each come with multiplicity 1 in the bottom, and so that's going to tell us a little bit about the graph too. So I've compiled that information that we've just gone through here on this next slide so that we can put everything together. So let's see, we've got two vertical asymptotes, one at that's the y-axis, and one will be x equals 2. So let's go ahead and put that x equals 2 one in here. And we've got the hole that's at 3, 4/3. So we'll put 3 and 4/3 up here. And we're going to draw a hole in there. And we've got a 0 at x equals -1. So we'll stick that in there. We'll go ahead and put our point there because we know that, that we have a root there. All right, so now we need to be able to figure out what's happening. Our end behavior we can't quite draw because we know that it's approaching the x-axis. We don't really know yet whether it's going to be approaching the x-axis from above or below the x-axis, and so we've got to think through that as we draw our graph. So this time, instead of working from the left to the right, I'm going to work with this point. Well, it's actually the only missing point that we have, the hole, and realize that because that hole is above the x-axis and I have no other zeros or discontinuities to the left of even that vertical asymptote 2, I'm going to need to stay entirely above the x-axis there. And so that's going to tell me that I'm approaching my vertical asymptote on the right-hand side by going up to positive infinity. And then as I approach my horizontal asymptote, which is my x-axis, it's going to be approaching it from above. Okay? So now I've got two vertical asymptotes here between 0 and 2. And since there are no other discontinuities and no other zeros in between 0 and 2, I'm either entirely above the x-axis or entirely below. Now I mentioned kind of in passing to pay attention to the fact that we have multiplicity 1 for each one of those factors in the bottom, which is telling me that my arrows are going to be ending up going in opposite directions. Another way we could try this out and figure out whether I'm above or below is to just pick some test value inside the 0 to 2 interval. So perhaps if we plugged in 1 and figured out, are we above or below the x-axis? If you do that test value of plugging in 1, you're going to get out a negative value. And so what you're going to find out, however you want to think through this, is that you're below the x-axis between the asymptotes. And so then you're going to have some sort of piece that looks like that. You've got to approach each one of the asymptotes from in between them going down to negative infinity. Okay? So we have one more little part to go, the part to the left of the y-axis. And so we know that we have a 0 there at -1. And so just like we mentioned here at the vertical asymptote of 2, the arrows are going in the opposite directions because of the factor that goes along with it being odd multiplicity. So the same thing's happening at 0. We've got odd multiplicity here, which is telling me that my other one is going to have to be up there above the x-axis. And so, another thing you could do, you could always try, you could always test a point to verify that as you're getting close to the vertical asymptote of the y-axis that you are in fact approaching positive infinity. So what's going to end up happening is we've got to go down there and cross at the 0. But then we've got to remember where our arrow goes because we have a horizontal asymptote, and for horizontal asymptotes with rational functions, both sides, the left-hand side and the right-hand side, are approaching that asymptote. It's not a one-sided horizontal asymptote. And so even though we had to dip below the x-axis there, we're going to have to come back up towards the x-axis, and that x-axis is going to be kind of like a magnet in some sense to hold on to that end arrow there so that we can complete our graph.